Hello, my name's Kian Wormsley. I work for Autodesk Research based in Switzerland, and I'm here to talk to you today about using WebAssembly with your APS applications. First, let's start with a safe harbor statement. So please don't make any purchasing decisions based on what you see today, which is especially important as I'm part of research. So what you're seeing is not in our products. So here's the title slide. So we're going to supercharge browser-based APS applications with WebAssembly. And this is really about taking C++ code from various libraries and creating WebAssembly packages via Emscripten and loading them inside APS. So one thing to note, you can find me on social media at KianW, whether on X or LinkedIn. So please do connect and keep in touch. So onto the introduction. So today we're going to take two C++ libraries in particular and build them into a Forma extension. We're going to take VASA, which is a voxel-based architectural space analysis package that I've spoken a lot about in recent years. And we're going to take SciDevs, which is a simulation framework based on discrete event simulation. And this second one is open source, and you can see the GitHub link there. So we're going to take these libraries and build WebAssembly packages from them, and we're going to effectively load them as extensions inside Autodesk Forma. Now, what I'm showing today is completely valid for the APS Viewer and Tandem as well. In fact, I've also done very similar integrations with those, but we're going to focus on Forma because it has a very simple extension interface capability that's going to make that easier. We're going to look at three integration scenarios in particular. So the first one is just taking our voxelization engine and loading it into Forma in order to do real-time augmentations of Forma. So to create a responsive user interface that can do pathfinding, visibility, and shadows, but do it in a very real-time manner. The second one is a little bit more offline. Of course, the analytics we're going to run are in the browser. These are the human-centric metrics. But there's going to be a delay. It's going to take 20 or 30 seconds to compute, and then we're going to show the results. So it's a little bit more offline, less real time. And then the third one is very lightweight simulation, multi-agent simulation in the browser using both VASA and SciDevs. And in this case, it's really much more about graphics throughput. Now we can optimize for that. And with that, here's the agenda for today. We're going to take a very quick look at VASA and SciDevs. We're going to talk about Emscripten and WebAssembly, introduce the Forma SDK, and then we'll do some demos and conclude at the end. So VASA and SciDevs. So as I mentioned already, VASA stands for Voxel-Based Architectural Space Analysis. And it has various capabilities. This graphic is coming from Dynamo. So it's not publicly available as a C++ library, but you can use it via Dynamo inside Revit or in standalone Dynamo Sandbox. So it has the capability of calculating direct daylight and shadows. So that's one aspect. You can do visibility from a point. So there's a point inside the building, and we're effectively calculating the visibility outwards from there. Each of these things is calculated as its own voxel model. We can do travel distance from a point, and this is doing kind of a flood fill outwards from a point inside the building. And you can see the point itself just there, but we have a certain distance of travel from that point. And these are all, and the rust colored area are all the points that are accessible from that at a certain distance. We also have 3D pathfinding, so you can see a path that's been calculated through the building and going outside the building from this point to this point. And obviously, we need to be able to voxelize geometry, so you can import a mesh, whether it's an STL format or coming from the APS scene, and a scene from the APS Viewer, Tandem, or Forma, and we can voxelize it and then work with it. So that's an important feature. And at that point, we can also then do a number of typical operations, whether it's surface related, solid related, or fill operations or Boolean operations on various voxel models. If you'd like to learn more about VASA, please just head over to my blog, kianw.com. You can search on YouTube under the Autodesk Research channel as well, and you'll find a number of introductory videos. So SciDevs is not a toolkit that I've talked much about in the past, but it's something that Autodesk Research published some years ago, made available in order to facilitate simulation. It's an implementation of devs which is symmetrical. So if you'd like to learn more about that, then there's a number of really good examples on the GitHub site that I mentioned earlier. So please go ahead and take a look. All right. So with that, let's introduce Emscripten and WebAssembly. So Emscripten is an LLVM-based compiler that effectively takes C or C++ code and targets the web with them via originally ASM.js and now WebAssembly. So ASM.js is a subset of JavaScript that's really optimized for running transpiled memory managed code. So Emscripten is a transpiler. It takes code that is memory managed, such as C and C++ code, and generates this runtime code from it. Now, back in 2017, the primary target for Emscripten was switched from ASM.js to WebAssembly. So ASM.js as a project has basically been deprecated at this point in favor of WebAssembly, though it's occasionally still used by applications as a fallback. Emscripten's been used to port a number of very consequential C and C++ code bases to WebAssembly, so Unreal Engine, MeshLab, Bullet, and important from our perspective, AutoCAD, which we'll talk about in a bit. So WebAssembly is obviously a way to package code for execution on the web. You can think about it as being a bit like, a WebAssembly package is like a DLL that you can use inside a browser-based application. So, WebAssembly is often abbreviated to WASM, and it's a binary instruction format for stack-based virtual machine. WASM is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. So, as I've said before, it's typically built from compiled memory managed languages such as C++ and Rust. Today, there's very widespread browser support in all the main browsers, and it's increasingly popular on the back end as well. So you can use something such as WASM Cloud to execute WASM in the cloud. So Autodesk first started using Emscripten back in 2015, 2016. So the AutoCAD team created a DWG viewer using code that was extracted from the AutoCAD codebase. And at the time, we were targeting ASM.js. In 2017, we switched across to make use of real DWG itself, still using ASM.js as a target. And we gradually sort of built in more features such as measurement and basic drawing primitives such as lines, arcs, and circles. Then in 2018, we released our first version of AutoCAD for web that was based on WASM, and that was highlighted at the Google I/O conference in 2018. So let's talk a little bit about building a WebAssembly package with Emscripten and what's involved. You can see my terminal window on the right, where we've got the Emscripten SDK installed and we've activated it. And then this is our build script where we're going to be basically calling EMCC, and we'll look at the details on how that works later on. So effectively you're calling the Emscripten compiler EMCC, and it's going to go through, compile our C++ code, use our bindings, which is a source file that's just telling Emscripten how to take C++ features and expose them via WebAssembly. And once that has finished, we can basically see that we have a number of source files that are a number of output files that are created in our directory. And there you can see an HTML loader, which is just a test environment really. And then vasa.js, which is a loader for the vasa.wasm file. Now, during the compilation process, you very often early on in particular find that you're missing some bindings. So you'll get an error that says, yes, this particular type was not found and is depended upon. So you can use a tool called LLVM CXX to unmangle those names. So here you can see at the bottom, effectively, we're calling the CXX filt and, oops, excuse me, And this is a name that we want to unmangle, and we can see it's being unmangled to essentially be a standard vector of longs. Okay, so let's take a look more at how we use EMCC and what the various options are. So typically you'll use it with the embind option in order to create your bindings. That's the first thing. But in our case, we're also targeting something with an HTML extension. So in our case, it was vaso.html, but you choose the name that you want, and it's going to create an HTML file, but also a JavaScript loader for your .wasm file as well. So that's very important. In this case, we're specifying the most aggressive optimization level for Emscripten to use. And it works just fine. I mean, Vasa is probably like I forget if it's 12 or 15,000 lines of code, and you're creating a 400K WASM file with the most aggressive optimization level. One downside is that you're not going to get very descriptive errors when you get runtime errors with this level of optimization. So yes, you'll just get some numbers back which aren't very meaningful, but it's certainly for a production application that's been well tested. You shouldn't, need you can go with that level just fine. The next line is saying that we want to disable something called tree pruning for this particular module. So because we're creating a library with a number of functions that are exposed and objects, etc., we don't want the Emscripten to prune away unused functions, because not everything is going to be used by the library itself. So we're essentially using the whole archive flag to specify that for this particular input file, we don't want to optimize it. So that's very important as well. Yeah, because otherwise what you're going to end up getting is a really small WebAssembly package that doesn't do anything at all. All right, so the next thing is to enable, in this was important for Vasa. It's not necessarily going to be important for every application, but we need the ability to expand the memory that's allocated to the WebAssembly module. So we allow memory growth, and we also enable big integer support. This, I think, is going to be something that comes as standard in due course with WASM 64, but for now at least, we have to enable it specifically. Now, the last two lines, 6 and 7, are separated a little bit now because they're optional. Effectively, this is a way to do a bit more error checking and catch exceptions. So this is, you probably want to change the optimization level in order to get something meaningful out of this, but it's worth catching exceptions, which will add to the payload size for sure. Now, the last bit about creating TypeScript bindings, it's not at all, you may not care about people using TypeScript to implement code with your library, but enabling this does some additional checking. So it's kind of useful because you'll end up finding bugs or things that haven't been exposed via the bindings file that would not have been picked up otherwise. So I do recommend enabling that. Okay, so that's the build script. Now let's take a look at our bindings, which is really in many ways where the magic happens, because it's in this file that we specify which C++ features we want to be exposed via WASM. So here we're talking about a top-level namespace with a particular library, and we are effectively taking a number of types. This is just a two-dimensional array of ints. This is a standard vector of world vector 3D, which is a C++ type that we're specifying. We don't have to go into details about what this type is. It will get just picked up and compiled via the standard C++ environment. And here we've got an optional type, because there's sometimes you want to be able to pass optional parameters to functions. They need to be registered as optional, and this is a world cuboid. Functions themselves are super easy to create bindings for. You just have to say, okay, what's the name? And then you pass in the reference or the memory address of that particular function. Otherwise, here we're exposing a particular class called my mesh class to WebAssembly. The thing to point out about classes, they're pretty easy to expose generally, and you can have multiple constructors defined for your class. But the important thing to note is they actually need to have different numbers of arguments. So here we have a standard constructor with 0 arguments. Here's a constructor with 1 argument, and here's a constructor with 2 arguments. So if you have multiple constructors with, for example, 2 arguments, you're going to need to find either add an argument in some way or find a way to differentiate it from differentiate between them, or you need to make a choice about which is the most important for the library to have exposed. But this is kind of a nuanced problem related to the fact that ultimately in JavaScript you're going to have functions with different numbers of untyped variables, so there's no way to differentiate between them. But it's an interesting and important point to be aware of. Okay, and there we just have another couple of functions that we've exposed from our class at the bottom there, nothing very complicated. Now, in the next example, we're taking a template class. So it's called my templated class, and in this case, we're specifying a type, in this case, bool. Now, Emscripten doesn't really support templates as such, so we could not expose that as my templated class of T. We just couldn't. But we can pin down that template and specify, okay, we're going to expose this one as bool. So, and that's an important thing to be aware of. The other thing that's worth, and it's not related to templates in particular, but this is just using this as an example. You may have an overloaded function which has different types, so you have different overloads of a particular function, and in this case the function is called overloaded, and we're effectively pinning down the version that we want to call with this overloaded function by using select overload and a particular return type. So it's going to choose that very particular version of the function to return. Now, the next 2 slides are really just talking about things that are slightly more advanced, really. You often might want to use custom marshalling of some way, and with the optional override class, you can do that. So this allows you to have your own piece of code that is effectively executed, and the C++ code. So here we have a function which is called do something with pointers. Now, pointers are not supported inside Emscripten to anything but primitive types. So if you have larger, more complex objects, in this case, we've got a list of my class objects. We can't pass in a list or a vector of pointers to my class objects. We just have to pass in the objects themselves, and then we just imagine you have a helper function which takes a list of pointers to objects and returns. It takes a list of references to objects and returns a list of pointers. And at this point, we can then call into our base function and return the results. All right. So the interface to do something with pointers is not taking pointers, but we can convert them to pointers and then pass them in internally. Similarly, and this is very analogous, is you cannot use a standard vector of bools with, and it's an arguable question. If you look on Stack Overflow, etc., ask ChatGPT, it'll probably tell you why in C++ it's a bad idea to try this anyway, to use a vector of bools. Because they can't. It's not a type that can be used as a you can use references for. So, but as it's not supported in Emscripten, here we're effectively going to we've got a function that returns a bool list in C++. We're going to call that, and these are our results, and then we're just going to use a helper function to translate our vector of bools to a vector of ints, and then we return that. Okay, yes, and there's a description of what that does. So yeah, here we're just returning a standard vector of ints instead. All right, so that's our bindings. Just a very quick note on how to load the WebAssembly module into your extension or APS module, etc. Here, this is just a little bit of boilerplate HTML. We're calling it via a script, an async load for our loader file. So whether this is Vasa.js or whatever the name is for your loader, then effectively what's going to happen is when this method is called, the on runtime initialized method is called, we are going to just store a reference to, oops, we're going to store a reference to that inside our as a property of our window object. And then within our JavaScript code, we can just reference into the window.wasm function in order to then call methods on it, create objects from it, etc. So it's fairly straightforward. It's just straightforward JavaScript after that when we want to use it. Okay, and with that, we'll move on to talking about Forma and its SDK very briefly. So in terms of Forma as a tool, obviously it's our latest offering in, for our customers in architecture, engineering, construction, and operations. So we are, in terms of Forma itself, it has the capability to bring in contextual data from a variety of sources for you to then work with at a site level and increasingly at a building level. You can then design, have access to a number of capabilities to design and to automate the design of your environment, and then you can run a set of analyses, whether these are real-time analyses that are just always being executed, or offline analyses that are a little bit more time-consuming. So, but the infrastructure is there for all of these. Now, in terms of a third-party ecosystem, you can integrate data into the environment with a custom data provider. You can, extend the authoring tools. So today we have additional connections for Revit, for Rhino, for TestFit, etc. And there's also the ability to integrate your own analyses into Forma. Now, in terms of what we're going to be making use of from the Forma SDK, and you'll often hear about the Forma embedded views SDK as well. That's another term that's used. So initially, we want to get some project data. We want to display some graphical information back to the user. We want to do some user input and some camera control. So in order to get geometry from the scene, in order to get the mesh information or otherwise the road information, etc., you can use get paths by category. And then if it's a mesh, you can use get triangles to get the underlying, the triangle representation of that mesh. You can ask a user to select a point on the canvas. So this is via the get point function. If you want to create meshes and then display them back inside the scene, then you can use add mesh and update mesh. If you want to have an overlay as a ground texture, you can add in your own HTML canvas and then update it. And we're going to be using all of these capabilities. And then the last one, you want to be able to move the camera so that you can navigate through the scene automatically. When you're working with Forma, I do recommend making use of the local testing extensions. So if you don't do this, you'll have to keep publishing your extension somewhere publicly and, relying on, well, publicly or internally, but still you have to publish it. Whereas local testing, once you've added it to your project, as we're doing here, it is then, if you bring up a window, it's going to then call up your extension files from your local system. So you will need to have a local HTTP server, which is either serving up on port 8080 for the left-hand pane or 8081 for the right-hand pane. And we'll be showing how that works in the next section where we're going into demos. All right. So as I mentioned before, we have 3 different examples and we're going to step through each one. The first one is taking VASA and using it. In this case, you can see the local testing extension being loaded from port 8080. This is our local file. So we're voxelizing the space. This is a view of downtown Amsterdam next to the building where the DevCon is happening. And here we're effectively going to do real-time pathfinding between these 2 points, a green point and a red point. And we can either use sliders or we can select on the canvas to choose those points. Now here, this is rudimentary pathfinding that happened, not just avoiding buildings. So you could see that it actually went across canals and waterways, etc. We then enabled the option to then just follow the roads because that's quite important for this area. The next thing we're going to do is to look at a visibility dome. So this is going to say from a particular location on the ground how much of the sky is visible. So it's using a voxel model. It's essentially using a visibility function. So to do visibility from a point in order to calculate how much of the sky is visible, and then we're creating a mesh back inside Forma to display that. And here we can change the size of the mesh. We can change some of its properties. We're putting it on the path, so as we follow the path, we'll be able to go through it. The next thing we're doing is checking visibility from different windows of a building that we've modeled inside this environment. So you've got a visibility cone. You can modify the radius and the length of the cone. You can also specify whether you want to show the cone itself or just the areas where it intersects with the geometry. And then we can just say, well, show me all of the visibility cones from every window of the building, which kind of just shows overlays voxels on all the buildings around it from there, which is kind of interesting. And then finally, we're using the VASA to show real-time shadows. Now, because this is more intensive, because there's more shadows than anything, we've actually adjusted the voxel size. So increased the voxel size by a factor of 2 or 4, I think, in order to make that more performant. And now we're just going to follow the path to go through the space. So here we're cutting through our visibility cone. You'll actually see there are some areas where the roads were not perfectly aligned with the buildings. And I don't know whether that's a problem with the roads or with the buildings, but that is a slight quirk that you're going to see. But here we're going through and then just arriving at our red dot, which is the other end of that path before we reset. All right, so that was the first example, which is really about responsive UI and being able to do calculations quickly and return that information graphically to the user. And the next one is a bit more offline. So we created 3 human-centric metrics that use a variety of computations and analyses to effectively contribute to a measure or a prediction of how social, tranquil, or explorative a space will be. Now, if you're interested in learning more about this, please drop me a note because we're publishing a paper on this shortly. We have, in the left-hand side, you can see, this is just a debug view with various information in there. So you've got the red and yellow is about what daylight is able to come into this particular apartment. It's also, then we have a congestion map, which is there in purple. Now, these various indicators and others can allow us to assess how social a space is, how tranquil it is, or how explorative it is. And we're showing that information as heat maps on the right-hand side. Now, each of these takes about 20. So when we're, for these apartment sizes that we did the testing with, each of them takes about 20 or 30 seconds to calculate. So it's really not that time consuming, but it's time consuming enough that it's kind of an offline task, even if it's being done on the browser side. So it's a slightly different scenario. In the right-hand side, you can just see an animated GIF of the results of 20 different apartments that I've put in there just as context. This is not how it happens in real time. As I said, it takes 20 or 30 seconds for each of these to calculate. It's worth noting that Forma itself does not currently allow you to do detailed interior design. It's mostly sort of site level design. So we have created these apartments in a different environment. We've imported them via Dynamo into Forma, created meshes for each of the layers of geometry that we care about, and then load them into our extension. So this is, it's not currently working with geometry that's been created natively inside Forma, but over time we hope that we can switch to do so. Okay, and then the final example is around multi-agent simulation. So using the same apartments that we had inside the last example, we're using SciDevs to well, first of all, using VASA to voxelize the space and to create a couple of a number of sample points inside the space where our agents can be located. And then using SciDevs, we kind of randomly choose to move agents from their current space to an empty space inside or an empty location inside our space. over time. So the results themselves come back quite quickly from the simulation engine. We're just sort of playing them back, uh, inside Forma in order to see the movement of our agents. Now we can display the movement of the agents in a variety of ways. So these are using tracks, which is like sort of fading disks. We can also see paths, which in this case, a more persistent view of the paths that were taken through that space. And we scrub forward and can see that obviously more and more paths have accumulated over time. So that's an important thing to note. We can also uh, we're going to load in an additional model that has multiple stories. So here, um, there we go. It's just going to display now once we move the cursor off. I think I had to click that a second time to make sure it worked. And so yeah, this is a building that has two stories because for the one-story buildings, we had the roof removed, the ceilings removed to make it more visible. Here, we want to keep it there, but because we also added the ability to sort of stretch vertically a space to make it more obvious where the agents were. So the agents stay on the ground floor, but the space is stretched upwards, and then we can also adjust the transparency of the building so that the agents themselves are more visible. We can see them going up and down stairs. We can. One thing that I didn't point out in the last one is that there are these direction arrows. We have a cone on top of the agent to show where they're going. You can turn off the building. You can turn off the agents. You can turn everything off, actually, although it's a little bit less interesting. But here you can see just the paths being created. So this was just our exploration to understand what the capabilities were with Forma in terms of displaying meshes in a dynamic fashion, such as this. And I think, I will say overall it was pretty successful. We've been very happy with how performant Forma has been in that sense, because we're passing a lot of mesh information. This is not instanced geometry on the GPU or anything like that. These are in each of those meshes we're passing through vertices for each of them. One additional capability that we're enabled just for a bit of fun is the ability to follow a particular or a random agent during various movements that they make through the space. So whenever an agent is about to move, we choose whether to follow it, and then we can kind of go and have a first person view. Once again, using our ability to modify the camera to go ahead and do that. And then finally, I did want to just show this same kind of example, but with a larger building where we threw in 100 different agents just to see whether Forma could handle it. And it is a little slower, but it does, there's a lot going on here and there's a lot of movement. And you have to bear in mind that we're kind of, displaying the graphics for every single one of those agents on a frame by frame basis, because we made the decision to aggregate all the agents into a single mesh, which is something that I've blogged about, and it really was the best approach in terms of making this work. All right, so let's move on to a conclusion and sort of wrap up regarding each of these three different examples. So our three examples have very different considerations in terms of what we wanted to get them to do. So the first one is much more real time, doing quite complex calculations, but making sure that we, had a responsive user experience. So we wanted to make sure that latency was as low as possible. We wanted to reduce, in some cases, and the shadows is a great example, right? Because with a lower voxel size, it's going to take longer to compute, and it was also going to generate more triangles, which is part of the issue at least. We adjusted the voxel resolution to make the voxels larger, and so we could basically keep the latency down and keep the experience highly responsive. For the second example, which is more of an offline example, we had a long-running task that was running inside the browser. A couple of things to note there. In this example, when we coded it, we made the decision to just expose all the capabilities of VASA via through WebAssembly and then to use them inside JavaScript code. So most of our our metrics, our analytics are implemented inside JavaScript. What we could have done is if performance is a real concern, we could re-implement those in C++ and then expose a much smaller set of functions. We wouldn't have to expose all of VASA. We could just expose the high-level functions to calculate the metrics via our bindings. And the code would ultimately run more quickly. Now, obviously, you've got to consider that trade-off between who's working on C++, who's working in JavaScript, etc., in your development team. So there are the considerations to bear in mind. But I think, one potential future optimization for that work would be to re-implement the metrics in C++ and then just have a really thin JavaScript layer. In the meantime, one way that we made the offline metrics calculate and avoided tying up the main thread was to use background threads via web workers. So effectively, you can call it used. And this is also something that I blogged about. So the information is all there publicly, where you can effectively use a web worker to load in a particular file and make sure that the metric then gets executed on a background thread. And then finally, with the multi-agent simulation, the simulation itself is very basic at this stage. It's really just a proof of concept for us. So it runs very quickly, and you can either return all the results to be visualized. We either return them all at once, or we can step through them one by one. But the biggest challenge here really was around the throughput of mesh data in terms of just the volume of data we wanted to throw at Forma. Now, in our case, we experimented with a few different ways, like meshes for individual agents, etc. But that ended up being really unwieldy and cumbersome in terms of the overhead of figuring out which were being displayed or not, etc. So we ended up creating just a small number of high-level meshes, one for the building, one for the agents, one for the paths, one for the tracks, etc. And then just those are empty meshes at the beginning, but as soon as things get enabled and created, they get populated with all the vertex information. So that's the other way that we went with this particular example. And even though we're regenerating all the vertex information effectively on a frame-by-frame basis, we found that was the most efficient way to manage things. And even with 100 agents, the performance was pretty decent. So we love this combination of APS with WebAssembly. Today, we really focused on Forma, but please rest assured that everything I've showed today works just fine inside the APS Viewer and Tandem as well. I think this is an ideal combination of technologies for legacy applications or performance critical code that you may want to execute inside the browser. As you've seen, you can create highly responsive browser-based tools based on WebAssembly inside an environment such as Forma. Now, a last note is that while we're focused on C++ code today, you can obviously you can use Emscripten to build from C as well, but that's not the point. The point is that there are other tools that exist to build from other programming languages, whether it's Rust, whether it's from .NET, which many of you will be familiar with, and even Python. So Python is not a typed language mostly. And yet there are projects ongoing that would allow you to create WebAssembly code from Python as well. So there's lots of really interesting avenues for taking existing or new code and building it into WebAssembly to then be used inside the browser. And with that, I would just like to thank you for your attention, and please do reach out if you'd like to engage more on this topic. Thank you very much.